大家好，我是王不老说半岛。Hi folks, today I would like to continue my packaging process technology update. Today's focus will be backside power delivery network, BS PDN, and this is the part one. I think I should do a part two soon. The title was about AMD Xilinx, and then the race between TSMC, Intel, and Samsung is on about this backside PDN. So I would like to give you a quick summary of what's going on in the technology enabler behind them. All right. First thing first, let's do some quick review of why I think it's important to bring you into the topic. The first review is what is the big idea about what the big deal about the radical size. As I've shown before, 26 by 33 is a maximum size of a die that a ASML lithography tool can do. Right. And this picture is just for the high NA demo that I showed before. Currently, this is what has been done, and this is the size of the 4xAX is on the mask writer. That's a different story. Please go back to what I have mentioned before, or this link. The bottom line is this. So people use this universal measure. 26 by 33 is 858 millimeters squared. Is kind of a unit now. And can you do your patterning larger than this? Yes, it's possible, but you need to stitch them together, right? And if you times 6 here, that is because the TSMC say their packaging, they go in the future that they like to move to 5 or 6 this size, which is 5,000 millimeters square. And why this is important, okay? The second review I'd like to present here is that the die size really matters. The die of advanced node is getting larger and larger. Look at this simple calculation I have done before for you. It's going down. So the key message that the larger the die, the lower the yield. It's just about some statistics about particles landing on the wafer kills the die. So here you can see that theoretical calculations show that about even at say your 4 centimeter square, which is 400 millimeters square, that already give you 40%. So you can imagine that a die size of 8 centimeters square, right there. It remind you the maximum you can do is about 8.6 millimeters square. You cannot do that much, right? You at least some room around. So about 800 something, 820 is maximum you can do. And then you can see that the die you make has a lower yield, so it costs a lot more. TSMC is the only one who could do such a big die with a reasonably yield, which is less than 50%, right? And then you cannot improve it. That's given by the statistics, the best you can do. So you cannot say, I'm going to improve my process to make it yield like 80, 90%. That's impossible. All right. And then say you have a yield about half that you could do for the Apple small dies like Apple A13, something like that. So every die you got is very expensive. TSMC had to churn more wafer out, right? And then so imagine, keep that in mind. The larger the die, the more cost it come with it. And here is I mentioned it before, that the TSMC CoWoS update. They said currently this is, they could do 4x now, right? This is 4x. 2023, you could do 4x of the reticle size. And top one is earlier update. They said their integrated silicon packaging area is in reticle. In reticle means the 1x is 8.58 millimeter. Okay, so, and then in 2023, they are going to 4x. In the future, they would like to do 6x. And this is amazing, right? The larger the key message I would like you to take away is that the larger the interposer, the more crucial the little stitching. You need to stitch them together. And then the warpage issue is going to be big. So the size really matters. And if you look at the TSMC flow, they developed this chip-on substrate first. And then they found it's a very large warpage. As I explained this to you in the last talk I had with you, is that if you place a chip on a thin down substrate, the residual stress is going to be shared. Going to be shared means that the substrate going to fit it. They can fit it with this simple, reverse relationship. That the substrate feel the stress and it will bend, so they will be warped easily. Okay, so if the thickness is comparable to the chip being placed, so this idea, the learning, is wow, that's not good. So that's the reason they put on a thick wafer, right? Here is your cobalt, a chip on wafer on substrate, not chip on substrate. This is much thinner and this is much thicker. Okay, and now bring me to my story about what's the big deal of AMD and Xilinx. You look at the Xilinx. Xilinx in 2014, they present this in the ECTC. They work with TSMC, and they claim they have this arc cores, right? They have tons of paper around it. That's what they claim, and they will address this issue. This is issue I mentioned earlier here. Okay, that yes, there's warpage, huge warpage for the CO chip on substrate first approach. They claim they help TSMC to solve that problem. Okay, and well, not exactly all their credit. I mean, TSMC developed this by themselves, right? Of course, top dies are attached to the full thickness in the poser wafer. This is the key: full thickness, 375 micron or more, right? Depends on the wafer you choose. Wafer is 375 to 700 micron. Depends on what type of wafer you buy, but at least 375. And they claim they have this reconfigurable COW because the chip on wafer technology. They have patterns around it. Okay, all right. So this is a process. They claim they could a reconfigurable idea, whatever that is. It doesn't matter in here. Okay, it's fine. Just give them the credit. They have some IP patents around this. And that brings me to the subject today. They call their IP, right, stacked silicon interconnect. And they started using this silicon interposer a long time ago, 2022, 2012. They already did it, right, much earlier than what the other guys are doing right now, because they have to have it. They have put this FPGA on top of a lot of FPGA on the piece of silicon interposer, so they could do what they need to do. And they put the silicon interposer directly to C4. But that's that time. That's what's been done. And then they have this TSV already, so they already did it. And the reason they have to do that is because the die is so large. Even though currently the biggest die, VU19P, is pushing the limits of 558. That time, the product is XC7 VH580T. And this technology in 2012, that is the first one, the first the FPGA for the backside coming. That's what I meant, coming from the backside, because FPGA die is so large, it's just like chiplet. These are all chiplet now. You can see that's early stage, early development of chiplet technology that we talk about today a lot, right? And that time they see the 3IC technology landscape is like this, right? The chip level, device level, wafer to wafer, chip on to wafer level. All these, some are realized, right? Some are not. Monolithic have been still been talked a lot, but not really happening right now. And then the people are work the wafer on wafer, chip on wafer. These are all pretty much pretty good. TSMC is pretty good at doing that now. And then in the introduction of HBI, we talk about that a lot. The Ziptronics, right? That the inventor of hybrid bonding and the other company, so that or university developed these ideas. And Sony did a pretty good job in the product about the oxide-to-oxide bond. I'm guessing that's TSMC because Sony worked closely with TSMC for their image sensor. Right? So I think TSMC did that for them as well. So you can see that all these technology, who has the biggest customer group? It's TSMC. They learn from working with the customers with different concerns, and that's the reason they have a lot of IP available for the customer to use. And that brings the topic that, as we know, AMD bought the Xilinx for $35 billion. They're all stocks. This is Lisa, and this is this Xilinx boss. They bought, why AMD want to buy them? I'm asking this question. Why AMD want to buy FPGA? I think one of the reasons is that their packaging, they have a lot of IP around it. I think that should be a big part of it, in addition to other concerns. As I showing in the very beginning, that in this presentation 2014, and this is 2014 ECTC. Xilinx says that they have tons of patent around this CoWoS process technology. When the customer want to work with TSMC, TSMC can offer their IP, but usually the customer will provide their own IP to complement what TSMC can do for them, because that will be a key leverage as well. And so my thought process is that AMD buying Xilinx is for their SSI, a big portion of it. Why I think so? Well, let's look at their advertising. Okay, let's just look at this from their website. I downloaded, and you can see what I meant.
Attaining maximum performance. With the UltraScale Plus portfolio, we also introduced Smart Connect technology, a collection of IP and fabric optimizations to bring out the highest possible performance per watt from the silicon for your specific design.
Sorry.
Maintaining maximum performance. With the UltraScale Plus portfolio, we also introduced Smart Connect technology, a collection of IP and fabric optimizations to bring out the highest possible performance per watt from the silicon for your specific design. Smart Connect optimizations include new AXI IP interconnect optimizations, as well as what's called time borrowing that redistributes clock delays, along with register retiming and pipelining explorations to increase performance per watt of interconnect and timing critical paths. Together, these optimizations further raise the bar for performance per watt. So let's take a look at how this all comes together. Here, we've normalized performance per watt against our 28 nanometer 7 series products. For 20 nanometer UltraScale devices, due to both process and architecture enhancements, you typically see a 1 to 2 speed rate improvement, or a 1.2x performance boost. With that, you also see a power reduction, typically around 30%, for a 1.7x performance per watt improvement relative to 7 series devices. Now, for UltraScale Plus devices, at what's called nominal voltage, or VNOM, you get the highest possible performance, roughly a 60% increase relative to 7 series, with a 20% power reduction. That's double the performance per watt. But beyond VNOM, we're offering something unique that we've never done before. With the same piece of silicon, you can operate at either the nominal voltage of 0.85 volts or at what we call V-low, allowing you to focus on power consumption while still getting optimal fabric performance and critical transceiver and memory interface line rates. With V-low, you get a 1 to 2 speed grade advantage with a whopping 50% power reduction. Smart Connect technology takes it even further by yielding a 2.6x performance per watt improvement over 7 series at VNOM and a 3x improvement at V-low. And just to give a practical example, let's take a look at this large wireless radio design that we implemented with Smart Connect technology on a Vertex.
So the key message is obvious, right? When they move to a smart the key takeaway is this foil, right? Basically, they once you use the Smart Connect, the performance per watt boost is really significant, right? It's really significant, the best they can achieve. And so I think that's a major reason why AMD bought this Xilinx for their pretty much for their IP and learning. And then Xilinx also said that they have the patents on various process-related issues. Voiding and cracking happened during the process. They said they have many patent pending, so to address each issue. So the copper fusion, so for take advantage of this IMC's intermetallic compounds, and then so they have many IP around to solve these high temperature stage reliability issue that usually observed. So you can see that the customer company bring their own IP portfolio into their foundry to help them out to optimize the process. And that's the strength of TSMC working closely with their customers. And AMD bought the Xilinx, obviously, to me, is for the rich portfolio of the patents. Okay. In this IMC patent, they say you need to dope copper. If you dope copper very nicely, you form a special compound at the interface that will withstand this 1,000 hours high temperature test that is required. If you don't, you're gonna lose. You're gonna lose the bonding without this copper doping. Of course, TSMC probably have own IP as well, but this helped them to solve the problem. Then, so the bottom line is, why connect power from the backside? Now, the front side of VDD, we put it there. It's so far away from the silicon channel. And the IP drop is unbearably large for scale nodes. So this thing happens. So if you want to apply backside PDN, it happened at a 3 or 2 nanometer. You cannot do it now. The process too immature right now to do it. And so for the extreme node, that will do it for the 3 and 2 nanometer. But will it fill back 0.257? I think so. Once you master the process technology of backside PDN, of course you're going to bring it back to the front end to boost your whatever that you want to boost. And that is I think that's well known. And this one can really help out to extend the roadmap, because at 3.2, the IR drop is so large, you lose the performance so much. There's no point of scaling, because scaling doesn't help you. Scaling help you in the area, but you cannot say I want to. You have to keep the performance going at the same rate, say like 10, 15% boost or higher for each node reduction, right? You cannot say I have an area reduced, but my performance the same. Then the customer say, what's the big deal? You reduce the area, make it that a little bit smaller, and then you make more money, and I didn't get any boost. So you have to keep the performance boosting going to attract the customers. Then this one will let you have it, right? Pretty much. That people know that at 2 or 3 nanometer, especially 2 nanometer, it is required, okay, to use this technology as the scaling booster. Otherwise, the process uses. And Intel is all in on this. You can see on the right side picture that I downloaded on their website, the power and signal, all right? The power and signal are now used to be in one. The power and signal come from the top. This is your contact, your I/O contact coming in here, going through here, and then the transistor level is here. This is where silicon fins are, and then the signal you could do that, but what about power? Why you need to power to put them together? Because they have no choice. But the new technology separate them, separate the power from the previous power and signal. Power is power, signal is signal. That make life a lot easier. So, and that's what the vision of the BiCS PDN. And Intel really like it. They did. I think they are ahead of everybody at this moment. Everybody try to catch up, right? And then I will explain who did what, right? And later. And so the key message here, Intel ON for this one. They will do it in the 20 angstrom node, 20 angstrom node, but they had to make the 20 angstrom node work first, okay? But they use the Intel 4 test chip to prove it's working. So it's good. So I think they're ahead. They're really ahead. Then just look at the big picture. Why this reduce the, I want to do a simple calculation for you. Why it's a big deal that you want to move the power from the front to the back. Here's your VDD. What's the power of VDD? VDD is 0.7 volts, okay? So let's keep that in mind. Let's look at the graph on the bottom right. That you can see that at 32 nanometer node, your channel resistance is about the same as external. And then when you go down, actually the channel resistance reduced dramatically. The external is like the 2x now, right? But I'm not going to use this extreme case. I'm just going to use this simple case that at 32 nanometer node, the channel is resistance is the same as external. And then so my ID, how do I calculate the ID here? Is the VDD divided by resistance, right? So it's a simple calculation. And using this graph, this is sort of equivalent circuit diagram for you. That the pillar that we saw here is about 300 ohm per pillar, 300 ohm. The pillar means that here, all right? When you go down a VDD to all the way to here, all this pillar, the resistance is 300. When you go down to the transistor level, you see a resistance, say 170 micron per micrometer. Okay, that's whatever you have there at external. And then you go down to the channel, and that's how you drive your current, right? So it's a simple voltage divided by resistance formula for getting your current. And so using this one, and this is a loop, right? So that's why it's a factor of 2 here, right? Factor of 2 here, because it's a loop. So 0.7 volts, that's your VDD. And then you have your own channel. This is your channel, it's 170. And the rest is your routing around that channel. You will put this number here directly in, you get 0.6 milliamp per micrometer. And you get that. You could pretty much take that to the bank. Is what you usually see right now in any report. I will explain what is a per micrometer means later. Okay, bear with me. So this one is without PBN, without backside PDN. So the VDD had to come all the way to your transistor, and then that's the current you get. Now I'm going to estimate without the with the backside PDN, with the big, previously is without, now it's with. Then this is gone. This is gone. This is gone. Okay. And then the contact here, it's become 50. The backside rail coming here with it's much bigger and wider. So the resistance drop as well. So overall resistance become 50 and 2. Right. So here is, I'm sorry, 5. Here is 5. This nano TSV. I'll explain later. So your power coming from here. And then so the formula changed. The formula same. The numerical value changed. Previously it was 300, 170 and 300, right? And then now it dropped to 5 and 50. So the dry current become 2.5 milliamp per micrometer. It's a huge boost, right? Previously it was 0.6 milliamp. And now with the backside PDN, it's 2.5 milliamp. It is 4 times larger. So you can see all the report. Oh yeah, 80% reduction resistance, blah blah blah. Yeah, that's you can see that the simple calculation does show the benefit tremendously. Okay, and as I mentioned, what a per micrometer means, right? It's just FYI. Dry current is usually expressed in milliamp per micrometer because you are comparing different size of the fin, number of fin, and different size of the fin. Some fin are taller or shorter, so it's difficult to compare apple to orange. So people agree that we should use this. The evaluation of the current expressed in this is 1 micron equivalent width of FinFET design. I'll say it is 1 micron equivalent. So for example, 7 or 10 nanometer, the H fin, the height of fin is 35, and then the width is 6. So one fin has equivalent width, okay, of 76. So you have, this is about total to make 1 micro, say it's, oh here, I'm sorry, I calculated with, should be 4. Let me correct it. It means that to get 1 micron in width, you need a 14 fin to comprise of this to make it 1 micron. That's what it means. If you have a taller fin, then you need less number of fins. So when you measure your current, and that's how you're going to do. In this case, you measure 14 fin together, and then that's the total current you obtain from this. This is what it means, right? Because the one fin has 74, and you need 14 to make 1 micron, and so you measure 14 fin to get your current, and that's how you report it out. Okay, so that's what it means. So that's just give you a FYI. I hope you could, when you use it to read other people's reports and paper, it help you out understand what they try to say. And who came up with the backside PDN idea? It turns out it's IMEC and ARM. When they work together with the GTCO, they find this idea really works. Okay, power decoupled from the signal. Okay. They move the power distribution to the backside in a way so as that they could really reduce the resistance. Okay. And there are 2 ways of doing so. Okay, one is called very power rail, which is just a rail here. Rail is a very long straight line, right? Perpendicular to this to the surface you're seeing here. Very low, very rare. So previously, the front side PDN, this is what we saw, this POR process, right? The power and the power and the signal, let's ignore the signal now, signal didn't change. It's a power coming from the top all the way down. It's a front side PDN. Now they want to hijack it in a way, say, I'm going to intercept with a berry rail. You have the vertical one, it's called a vertical barrier rail. So all these kind of a connection go to the, say, metal 1 or metal 2. And then the distance for the power to go to the transistor is much shorter than the previous one from the top. Here it didn't say clearly, but here the distance is like metal 12. This is metal 12 all the way down to metal 2 or metal 1. And here, so you had to pass from metal 12 to metal 2. They're very thin line, by the way. So the resistance is huge. And here you have the barrier rail that go directly hijack it at, say, metal 2, right? So that's much faster. And for the backside BPR, for the backside PDN means that it combines this idea, all right? And then it all the way down with the backside now. And here they create more backside PDN network to control it. And then the barrier rail is right here. Okay, they move this one up and with a complex, adding more complex circuit in the back. And this one provide more control, more benefits. If we want to do it, I think I find a picture that's easier to understand. I give you more better picture. Is this one. The way to put your barrier power rail. And you can see that the green one is your fin. The rest is the source and drain gate. Okay, so let's ignore that for now and look at your backside, the barrier power rail for the front side PDN that we saw here is on the side of the fin, next to the fin. So there's a power rail here. So you do this reasonably easy. Here is a lot harder. Here, the backside rail, see, they flip it. They flip it already. So it's going this way. And this one is the barrier power rail with the backside PDN. And this barrier power rail with the front side PDN. This is your front side PDN. And this is barrier power rail. This 3D picture, I think, explained better. Okay. And if you look at more detail-wise, this is what I presented. My friend will also present this in a nice paper. And you can see that this is your POR process. Nothing changed. They did it until they didn't do I think metal 11. It's just they did demos. I think they did a demo at metal 1, metal 2. So they there's no backside process. They just initially started work on this already. So this is the backside, the barrier power rail. The reason they want to do it, I think the paper explained pretty clear. Because the area, half the each line in a standard cell, for this one, they eat up the area. So this one, if you do a cell design, it turns out it will eat up half the space. The width, half the width is eat up your cell the area. If you move it to the bank, you don't have a problem. And so, so they change it. So this is your backside barrier power rail. It replaced this white thin power rail in the metal 2. And that actually saved a lot of area and reduce the area loss. So basically, this is the idea. Not backside, sorry. It's barrier power rail reduce the area lost. So it's for that benefit. Previously, you have to take the the width of these POR power rail that actually eat up your cell area. And now you don't have to. So that's area reductions, and then enabling 5-track or small number of tracks for the nano sheets and all that. So that's a huge benefit, and why people have to go to BPR. And for the backside, and you provide more control, more complex to the BPR, you put it there, right? So here is more complex now. You access your barrier power rail with a backside, a complex backside with a backside metal 1 to metal 3, depends on your design, right? So this overall backside PDN, and I think would include this. This is a nano size TSV to connect your control network in the back to the power rail, to the barrier power rail. It's buried. That's why it's called buried power rail, right? And Intel call it Power V, by the way. They just want to be different. Okay, that's fine. And if you look at the IMAX, what they did, right? This is they come out in the talk. Okay, you could easily find online. So pretty much this is all standard process. All standard process. There's no surprises too much, except that the power rail, they have to use tungsten. Right? You cannot use copper. The reason is that it's too close to the channel. If you use copper, which can reduce the resistance even further, but you don't want to do that, right? Just like everything else in the metal one area, try to not metal one area, the contact area. You have to use non-copper, right? Cobalt or tungsten. Right now it's cobalt pretty much. But it's only present this paper is to demonstrate. You don't have the key process technology to do everything POR in foundry. That will be, there's no way you can do that. Right? They are not into the yield business. They're here to demonstrate. Okay. And then the one interesting is that the silicon germanium etch stop layer, which I explain later, they use that to stop the etching. They need to dig holes, right? They need to dig holes, and then we're going to stop because digging through silicon, you have to find another idea. So SIGI is the one they used, and there is a reason behind it because that's how you can do epi. So this is for the more complex one, the front side to the back side. So the first step they do is to take a wafer, and then they do an epi on top. The epi is 50 nanometer SIGI, and then you grow silicon on top. So this portion is they do an epi on top. And then after that, they build, of course, then you build a device on top on the epi you just grown. And you flip it with a carrier wafer. And you bound them. And here, before you're flipping it, you have to have IOD0, IOD layer, right? Some kind of oxide layer before you bond it, right? And then you eventually you thin it down and you create your backside in this way. So that's not going to detail. Here, I would just focus on two things: the SIGI epi and its impact to why I say it's not very easy for high volume manufacturing, the foundry. This is a foundry try to do high volume manufacturing. That's called SVM. At the end of the day, the SIGI is not there. SIGI as their stop is a sacrificial one. You removed it. So you don't see that. Right. Here you have a step to remove it. Here, that's the pink one, you remove it later. And so at the end, when you see the actual device, you don't see that. Here is your backside. Okay. Here you you close to the device here. This is a simple 4-pin device. Then the reason I said that I want to focus on to the Why it's so difficult for TSMC and Samsung to do it? So why can't I do it now? Just do it now, right? For current node. Well, it's not that simple. The reason is that I mentioned there are two problems with this, at least two problems. Here you have the CG, you had to put it there. But CG has an intrinsic problem. If you look at this thermoconductivity graph on the left, you will see that you need this thermoconductivity drop like a rock. It's a bathtub curve. So the silicon germanium that you use in here is at least 30%. This is at least 30%, right? To make it effective. Because you need to etch the stop somewhere. The material cannot say I'm using 1%. Then it's meaningless. You will not stop. It had to be an etch stop layer. The germanium content should be as high as possible. Let's just assume like 30% for the argument's sake. And actually, there's good reason for that. By the way, yeah, you cannot go over 30% because this is 15 nanometer thick. You cannot have germanium content too high, otherwise it will crack. It will form dislocations. So the germanium content is strong relationship toward how thick you could put it on. It's not an easy thing to do. So you cannot say germanium like 80%. It doesn't work that way. Then you cannot put 50 nanometer. Probably only 3 nanometer, 4 nanometer. You can put it on. So it doesn't work. So 30%, I would think is a good number to have. But if you look at 30% here, your thermal conductivity dropped from 150 to 15, 10 times smaller. Well, so what? You got some layer beneath your wafer and with a lower thermal conductivity. What's the big deal? The big deal is this. It has such a poor thermal conductivity when you subsequently for all the silicon process, there are many high temperature process. Right. For the CVD process, imagine for HDI, you want to tool to 1,000 degrees to get your HDI with a HDP, high density HDP work. You have to use very high temperature. And when you do that, you need to cool the wafer with helium. And imagine if you put an insulation on top, the wafer cannot be cooled properly. You have to adjust your process. If you don't do that, oops, then your wafer is hotter than you think. When the temperature of the wafer is hotter than you think, using the same process, you get definitely different results. So it's not an easy thing to do. And there are many other high temperature process that you need to adjust to compensate the CD. And so if you don't compensate, then your yield will definitely be low. So that's one thing everybody's work on. So you adding a new material to your wafer, every high temperature process that you have in your process has to be adjusted and readjusted. And that's your TD work. It's not a simple thing. And here is another one. The wafer to wafer low temperature bonding. It's not easy to do, as we saw here, as we saw earlier. You need to have this. This two layer had to bond together. They have the same material, right? This is, I think, SiO2 to SiO2. To bond them perfectly together is a big business. That's why Soitec is in business. They are doing a very good job in forming a SOI wafer, right? And if you have any debris, any particle, any defects, then you're going to impact. If you have big particle sitting here, you cannot bond properly, become a bubble, and you need to anneal it. That's why it says a low temperature, because but that's not going to work. Low temperature bonding is ideal world. You bond them together, you wash it, and you bond them together with some kind of a pre-treatment like plasma and all that. Yeah, fine. You bond together and you use it using a low temperature bonding process. You could bond it, but can you guarantee with a high yield? That's the key. That's the key. If you do the in the Soitec SOI business, their bonding temperature is reasonably high, so they can put bond very clean, very nicely, so become very flat. If you do low temperature bonding, the temperature, I don't know what you mean by low temperature bonding. You could bond anything without even heating up. If these two surfaces so perfectly clean, you could bond it in room temperature very easily. Okay. And you will not open it up, but you just will not survive later. Okay. So the low temperature, meaning 1 to 200 degrees, you could bond it reasonably good, but that's not good for HBM. HBM means that everything has to be perfect. If your bonding is not perfect, then the process screwed. So with that in mind, that's the reason I would say that HBM race is on. Intel, Samsung, and TSMC, they are all working very hard and trying to make this thing work. Everybody agree that's the thing you should do. But the question is, but the issue is, can you really do it? These Intel, their plan say, I'm going to introduce my power via backside PDN 2024. And they claim they will put competitor 2 years behind in this process. I think that's true too. That's pretty much true because and they did much earlier, and then Samsung and TSMC. Samsung is very far behind. TSMC is trying to catch up, right? And one of the report, if you look at it, they say that wow, that you think that the heat is a problem, and they would say you would imagine that you sandwich transistor in the middle of the chip, right? And then you had a lot of polishing in the backside, and you think it will be not an easy thing. It will not be easy thing to do. You would think it will be yield is gonna be not good, but it turns out they use Intel 4 process, and it worked very good. The yield impact, the performance impact, the performance is expected as good as they expected, and then the yield impact, how they qualify their process on the test vehicle seem very good. They're very happy with it. Okay, so that's the reason they say, yeah, my process are 2 years ahead of TSMC. Okay, so that's what they claim. But to make it work, you have to you don't use on Intel 4, right? You have to use on Intel 2, which is 20 angstrom, and that's a different story. So, but anyway, that's what they claim. And Samsung, on the other hand, come up with a Korean paper, and I cannot find that paper. They mentioned it, but I couldn't find it. And then they even recycle iMac picture here. Okay, that put me to think that Samsung it's not ready. Of course, it's not ready for sure. But how far away they are from the TSMC Intel? It looks like they are they are behind because they didn't come up with a decent paper to explain what they did, right? And TSMC, they this is what they announced. They say I'm going to do 2 nanometer in 2025, and the backside PDN will be delayed to 2026. The delay is a good thing for them because this is what TSMC always do. Is always make the device work first. Because as I explained, backside PDN is really hard for HBM. You don't want to do many things. You don't want to do many change at the same node. What you want to do is to make the node work first. You make the node work first. The 2 nanometer is working with a good performance. The die is good. The yield is good. Then you add your backside PDN. I'm not clear what the Intel will do. It seems they are doing everything at the same time. All right. Maybe they are doing the same thing at TSMC, but I just don't get a clear picture. They might do everything at the same time, which is very high risk, I must say. Don't do that, Intel. Please, took the learning that do the 20 AM 2 nanometer first, make it work, and then put backside PDN. I think that's what they're doing, by the way. All right. And Samsung is struggling. All right. It's not an easy process to do, as I explained. Okay, so that pretty much conclude what I have done here with part one. I explained the AMD, the reason why AMD buy the Xilinx with my personal perspective, and the race is on. I give you a simple picture about the size of the chip, the die, and then what the benefit of XIPDA in terms of dry current can be boosted very significantly in a simple example. Okay, I hope you enjoyed it. All right, thank you very much.